That glowing cloud in Orion's sword is not what it seems. We are about to journey into its heart to uncover 50 of its strangest secrets. You will discover why this beautiful nebula is actually a cosmic battlefield, a chemical factory, and a graveyard for stars. We will find shapes that defy explanation, violent explosions hidden from sight, and ingredients for life brewing in the chaos. By the end, you will never look at this familiar patch of sky the same way again. What do you believe is waiting for us in the dark? Our first stop is a cosmic illusion that has fooled astronomers for decades. Near the bright stars of Orion's belt, a target for backyard telescopes reveals something profoundly strange. Catalogued as the red rectangle, this object is a perfect example of how perspective warps reality in space. From our distant vantage point on Earth, we see a geometric, box-like shape glowing with a deep, ruby red color. But this is a trick of the angle. We are looking almost directly down the barrel of a colossal hourglass. Two vast cones of gas and dust, ejected from a dying star system, extend in opposite directions. Our line of sight peers straight into the hollow center of this structure, with the dense walls of the cones creating the illusion of a rectangular frame. The intense red glow comes from a specific process. Hydrogen gas within the nebula is being bathed in ultraviolet radiation from the central stars. This energy excites the hydrogen atoms, causing them to fluoresce with a characteristic crimson light, much like the neon in a vintage sign. At the heart of this ruby hourglass lies a binary star system, two stars locked in a tight gravitational dance. Astronomers believe this duo is the architect of the entire spectacle. As one star ages and begins to shed its outer layers, the gravitational pull and orbital motion of its companion star funnel that ejected material into two opposing jets, shaping it into those precise conical outflows. Surrounding the stars is a thick, dusty disk like a cosmic bagel, which further constricts the outflow and helps sculpt the remarkably sharp edges of the nebula. This combination of binary dynamics, a restricting dust disk, and powerful stellar winds is what carves this fleeting masterpiece. The red rectangle is not a permanent structure, but a brief, brilliant chapter in a star's death, a geometric ghost that will dissipate into the void within a mere cosmic blink. It reminds us that the universe is a master of perspective, hiding its true, wondrously three-dimensional shapes behind simple silhouettes. And this is just the first of many illusions waiting for us in the nebula. This geometric ghost is just one layer of the nebula's complex reality. If we shift our gaze slightly, we encounter a feature so prominent it defines the entire southern region of the nebula, a brilliant, sharp-edged ridge of light called the Orion Bar. At first glance, it looks like a solid wall, a celestial rampart built from starlight and gas. But this is no static structure, it is a front line in a relentless war. On one side, you have the blistering fury of the trapezium stars, a tight cluster of young, massive suns unleashing a torrent of ultraviolet radiation. On the other side, a cold, dark bank of dense molecular gas and dust, a cosmic cloud so thick it could form new solar systems. The Orion Bar is the glowing, ionized boundary where these two forces collide. This violent interface is what astronomers call a photon-dominated region. It is a place where light itself, in its most energetic form, dictates the physics and chemistry of everything it touches. The ultraviolet photons from the trapezium act like a cosmic blowtorch, slamming into the dense cloud. They strip electrons from atoms, a process called ionization, which causes the gas to glow with that characteristic luminous edge. But the action does not stop there. As you move deeper behind the bar, away from the direct stellar fury, the radiation field changes. The most energetic photons get absorbed right at the surface, creating a layered zone of destruction and creation. Just behind the brilliant front, the remaining ultraviolet light still penetrates, but it is now less energetic. This light cannot break atoms apart, but it can break molecules apart. It shreds simple molecules like molecular hydrogen, creating a soup of reactive atoms and radicals. This is where the magic happens. In this turbulent transition zone, the broken pieces are constantly slamming into each other, driven by the energy of the starlight. Simple atoms like carbon, oxygen, and hydrogen get forced together into increasingly complex unions. Through a frantic dance of destruction and recombination, they form molecules that are the precursors to the building blocks of life, things like carbon monoxide, water, and even simple organic compounds. Think of it as the universe's most extreme chemistry set. The Orion bar is not a wall. It is a giant, roiling laboratory where the raw energy of newborn stars is literally forging the ingredients for future worlds. It is a cosmic refinery operating at a scale we can scarcely comprehend, and it is happening right now in that beautiful, deceptive ridge of light. But the Orion bar is not the only structure being sculpted by this stellar hurricane. Drifting much closer to the fury of the trapezium cluster are far more delicate and precious objects, the proplyds. Short for protoplanetary disks, these are the glowing, embryonic cradles of new solar systems. The Hubble Space Telescope revealed them as breathtaking, tear-shaped objects, each with a dark silhouette at its heart. That central shadow is a young star, perhaps only 1 million years old, surrounded by a vast, spinning disk of gas and dust. This disk is the raw material from which planets will coalesce, a cosmic construction site for future worlds. Yet here in the nebula, these fragile nurseries are under siege. The intense ultraviolet radiation and powerful stellar winds from the massive trapezium stars act like a cosmic sandblaster, violently stripping away the outer layers of these disks. The proplyds closest to the cluster glow brilliantly, their gas ionized into luminous halos with long, streaming tails of material being blown away into space like smoke caught in a gale. It is a race against time. Can planets form from the remaining material in the disk before the entire structure is evaporated away by its brilliant, deadly neighbors? This violent environment may actually limit the kinds of planetary systems that can survive here, perhaps preventing the formation of gas giants that need vast amounts of material. Each proplyd is a snapshot of both creation and destruction, a solar system being born inside a storm. And in the shadows of these newborn stars, we find structures that seem to tell the opposite story, a tale of dissolution on a staggering scale. Scattered throughout the nebula, particularly in its slightly quieter outskirts, are thousands of mysterious objects dubbed cometary knots. From a distance, they look exactly like a swarm of comets, each with a bright, condensed head and a long, faint tail streaming behind it. But these are not icy bodies from the outer solar system. Each knot is a colossal globule of dense gas and dust, so massive it could contain the material of an entire star system. Their brilliant heads are where the ultraviolet light from distant hot stars strikes the dense gas, causing it to glow, while their long, streaming tails are shadows, pointing directly away from the source of the destructive radiation. The leading theory is hauntingly beautiful. Astronomers suspect these knots are all that remains of a once giant, ancient protoplanetary disk, perhaps from a very massive star that formed long before the trapezium. That vast disk has been shattered over eons, fragmented by radiation and shockwaves into these individual, dense clumps, which are now slowly being evaporated away one by one. So while the proplyds are solar systems trying to form in a hurricane, the cometary knots may be the ghostly remnants of a solar system that failed, or perhaps simply finished, its grand construction project long ago, its ruins now being slowly erased by the same light that once helped give it birth. Together, these two phenomena bookend the cosmic cycle, showing us the fragile beginning and the inevitable, luminous end of structured material in this chaotic nursery. The delicate balance of creation and destruction within the nebula is governed by a single, brilliant powerhouse. At the very heart of the Orion Nebula lies the Trapezium cluster, a tight-knit family of hot, young stars whose fierce energy illuminates the entire cosmic cloud. But even this familiar stellar nursery holds profound anomalies. The brightest and most massive member is a star known as Theta-1 Orionis c. It is a monster, shining with the luminosity of over 200,000 suns and driving the nebula's glow with its blistering ultraviolet radiation. Yet its most startling feature is an invisible one, a stellar wind of such ferocity it defies easy explanation. This star is blowing a hurricane of charged particles into space at speeds exceeding 2,000 kilometers per second. The force of this wind is colossal, carving vast cavities in the surrounding gas and shaping the nebula itself. Astronomers struggle to fully model the mechanisms that can launch such an extreme gale from a single star, making it a relentless and mysterious engine at the core of everything we see. This stellar powerhouse is not alone, and its companions tell a story of a more complex birth than we once believed. When scientists measure the ages of the trapezium stars, they find a puzzling spread. They are not all the same age. While most are around 1 million years old, a tantalizing few appear to be significantly older, perhaps by several million years. This suggests the cluster did not form in a single, brief burst. Instead, star formation here may have occurred in distinct waves or pulses over an extended period. Imagine a cosmic construction site where the first crew arrives and builds a few structures. Then a second, larger crew shows up millions of years later to finish the job, all on the same plot of land. This age anomaly challenges the simple picture of a cloud collapsing all at once, hinting at a more staggered, episodic history of ignition within the nebula's dense heart. But the greatest mystery of the trapezium cluster is not what we can see, but what we cannot. By carefully tracking the motions of the young stars swarming in this region, astronomers can calculate the total gravitational pull holding them together. When they add up the mass of all the visible stars and gas, the numbers do not match. There is simply not enough normal matter to account for the observed motions. The cluster should be flying apart, yet it remains bound. This is the Orion Nebula cluster's missing mass problem. The gravitational glue is far stronger than the visible material can provide. The leading explanation points to the presence of a large amount of unseen mass, likely in the form of countless faint, failed stars known as brown dwarfs, or perhaps even vast reservoirs of cold, dark gas that telescopes cannot easily detect. Some have even speculated, though it is a far more remote possibility, that the cluster could be held together by the gravitational influence of dark matter, a component not typically associated with such a young, open cluster. This invisible scaffold, whatever its true nature, is a silent, massive secret keeping the nebula's brilliant heart intact, a hidden architecture behind the luminous spectacle. Behind the brilliant spectacle of the trapezium lies a far colder and darker reality. The glowing nebula we see is merely the illuminated skin of a much vaster, invisible beast known as the Orion molecular cloud. Within this colossal reservoir of cold gas and dust stretching for hundreds of light years, lurks a particularly dense and active spine called Orion molecular cloud 1. This is not a cloud in the fluffy, cotton candy sense. It is a filament, a snake-like river of molecular gas over a light year long and unimaginably dense, so thick that not a single photon of visible light can penetrate it. To our optical telescopes, this region is a blank void, a dark patch against the nebula's glow, but this darkness is an illusion of profound activity. Using radio and infrared telescopes, astronomers have peeled back this opaque curtain to reveal the truth. The OMC-1 filament is a bustling, hidden highway of stellar birth. It is crammed with dense cores, which are compact knots of gas and dust so massive they are actively collapsing under their own gravity. Each of these cores is a secret stellar nursery, a cocoon where a new star, or often a whole cluster of stars, is beginning to ignite, completely hidden from our prying eyes. The entire structure thrums with the low-energy vibrations of cold molecules, a cosmic hum detectable only by instruments designed to listen to the universe's whisper. This filament is the true engine room of the Orion complex. While the trapezium stars are the brilliant, visible offspring, they were born from material just like this, and they are now blowing bubbles and carving cavities that will trigger the next wave of star formation along the filament's length. It is a self-perpetuating cycle. The violent death of massive stars and the fierce winds of the young ones create shockwaves that compress the surrounding molecular cloud, squeezing filaments like OMC1 until new cores collapse and new stars flare to life. So the beautiful Orion Nebula is just a temporary blister on the surface of this far greater, darker, and continuously churning entity. The visible glow is the flash of a fireworks display, while the molecular cloud is the vast factory and warehouse where all the explosives are made. Our understanding of this hidden architecture forces a complete shift in perspective, revealing that the most important actions in this cosmic drama are often taking place offstage in the silent, lightless depths. Deep within that opaque molecular cloud lies evidence of a recent cataclysm, hidden behind a nearly impenetrable wall of dust in a region astronomers call the Becklen-Neugebauer-Kleinman low area. A cosmic explosion of staggering violence occurred just 500 years ago. This event was so powerful it is still unfolding today, a slow-motion detonation we can only witness through the eye of infrared astronomy. While the nebula's visible face glows serenely, its dark heart conceals a battlefield. The trigger remains a mystery, but the leading suspects are two profoundly dramatic possibilities. The first is a stellar collision, a direct head-on crash between two young, massive protostars that were still forming within the dense cloud. The second is a massive instability within a single, gargantuan disk of material surrounding a newborn star, a disk that simply became too massive to hold itself together and violently fragmented. Whichever scenario is correct, the result was the same, a titanic release of gravitational energy. Imagine the force of 100 supernova concentrated into a single, chaotic point. This explosion did not unfold as a spherical blast wave. Instead, it functioned like a poorly made firework, channeling its unimaginable fury into narrow, focused jets. These jets are not made of light, but of solid matter, colossal bullets of dense molecular gas, each weighing many times the mass of our entire Jupiter. They were launched at speeds exceeding 400 kilometers per second, supersonic projectiles screaming through the surrounding cloud. For centuries, these bullets have been traveling outward, and we can now trace their path. Infrared telescopes peer through the dust to reveal dozens of these gaseous cannonballs, each leaving a glowing, shocked wake in the cold hydrogen as it plows through the molecular cloud. They are spread out like shrapnel from a grenade, some traveling in one direction, others in another, mapping the chaotic geometry of the initial detonation. This is not a historical event confined to textbooks, it is an ongoing phenomenon. The bullets are still moving, the shock fronts are still expanding, and the cavity carved by the explosion is still growing. We are witnessing the aftermath of a stellar-scale catastrophe in real cosmic time, a crime scene where the evidence is still flying away from the point of impact. This single event likely scrambled the entire local neighborhood, disrupting the formation of other stars, shredding potential protoplanetary disks, and injecting turbulent energy into the cloud that will affect star birth for millennia to come. The serene nebula we admire on a winter night is in part a beautiful scar tissue growing over a wound that is still very much open. Yet within that same dark cloud of violence and cold gas, a completely different kind of kitchen is operating. Tucked inside the Orion molecular cloud, one filament is a remarkable pocket of warmth known as the Orion hot core. This region is only about 1/10,000th of a light year across, impossibly small on the cosmic scale, yet it is a frenzied chemical reactor. While the surrounding cloud is a frigid -260 degrees Celsius, The hot core is a toasty 100 degrees above absolute zero, heated from within by the intense radiation of deeply embedded, newly formed massive stars. This temperature difference is everything. In the cold, dark outer cloud, atoms and simple molecules like carbon monoxide stick to the surfaces of tiny dust grains frozen in place. But here in the hot core, the rising warmth acts like a cosmic defroster. It energizes these frozen mantles, causing the ices to sublimate directly into gas, releasing a rich soup of molecules into a dense, turbulent environment. This creates a pressure cooker for interstellar chemistry. The released molecules are now free to zip around at high speeds in the warm, thick gas, colliding and linking together in ways that were impossible when they were frozen solid. The result is an astonishing molecular zoo. Radio telescopes tuned to the specific frequencies of molecular rotations have identified a bewildering array of compounds. We find simple alcohols like methanol, which is essentially wood alcohol. We find dimethyl ether, a molecule used in some aerosol propellants, but the list grows far more intriguing. Molecules like methylformate, a compound found in the scent of raspberries, and glycolaldehyde, a simple sugar, have been definitively detected. Even more complex chains like ethyl cyanide are present. These are not just random chemicals, they are prebiotic molecules, the direct precursors to the amino acids and sugars that form the backbone of proteins and DNA. The hot core is demonstrating that the universe is not just capable of making the simple building blocks of life, it is actively and efficiently assembling the intermediate steps in places of extreme stellar birth. Every one of these complex molecules is a tiny, vibrating testament to a fundamental cosmic process. The chaos of star formation, with its intense radiation and shocking violence, does not just create new suns, it also stirs the primordial pot, forcing simple atoms into the elaborate unions that could one day, on a distant, sheltered world, become the spark of biology. This means the ingredients for life are not a rare accident, but a standard byproduct of the universe's most energetic events. The chemical richness of the hot core is just one ingredient in a far larger recipe. To truly understand the structure of the Orion Nebula, we must step back and view it as a whole, revealing a colossal, invisible framework shaping everything within it. Enveloping the entire glowing cloud is a vast, diaphanous structure known as the Orion Veil. This is not a distinct object you can point a telescope at, but rather the outer skin of the nebula itself, a thin, wispy sheet of gas being steadily blown outward and ionized by the relentless stellar winds from the trapezium cluster. Think of it as the nebula's expanding atmosphere, a cosmic bubble wall on a truly monumental scale. For a long time, this veil was simply considered the boundary of the excitement, but recent studies have peeled back its layers to reveal its most crucial component, a hidden skeleton of magnetic force. Astronomers have mapped this veil by studying a subtle property of its light called polarization. As starlight scatters off the tiny dust grains mixed within the veil's gas, it becomes polarized, meaning its light waves vibrate in a preferred direction. The specific pattern of this polarization acts like a cosmic compass, tracing the orientation of the magnetic fields that thread through the material. What these maps reveal is astonishingly organized. Instead of chaotic tangles, the magnetic fields around the Orion Nebula are largely ordered and coherent, running like giant, invisible rails along the length of the molecular cloud filaments, including the massive OMC1. These fields are not just passive decorations, they are active architects. Their immense strength guides the flow of material, channeling gas and dust along specific pathways as the cloud collapses. This magnetic guidance helps dictate where dense cores can form, and may even regulate the final mass of a newborn star by resisting the inward pull of gravity. The fields also influence the spectacular outflows from young stars, collimating their erupting jets into narrow, focused beams rather than letting them spray in all directions. The Orion Veil, therefore, is far more than a simple boundary. It is the visible tracer of an immense and powerful magnetic scaffold. This invisible latticework provides the hidden structure against which the entire drama of star birth, from the collapse of dark clouds to the eruption of brilliant proplyds, must play out. It is the universe's way of bringing order to chaos, using lines of magnetic force to write the blueprint for an entire stellar nursery. This invisible magnetic scaffold gives shape to the nebula, but our very perception of its place in the sky is built upon a cosmic coincidence. Look up at the constellation Orion, and you will see 3 faint stars hanging from his belt, an alignment known since ancient times as Orion's sword. The middle star of that sword appears fuzzy to the naked eye, a smudge of light that telescopes reveal as the magnificent Orion Nebula. For thousands of years, every culture that charted the heavens saw this as a connected structure, a celestial weapon forged from 3 stellar jewels and a glowing mist. The truth, revealed only by the precise measurements of modern astronomy, is a profound lesson in perspective. These 3 stars and the nebula are not neighbors. They are strangers drifting in the void, lying at staggeringly different distances from Earth, only appearing to line up from our solitary vantage point. The star at the top of the sword, known as Mesa, is a blazing blue giant nearly 1,100 light-years away. The nebula and its trapezium stars are roughly 1,340 light-years distant. And the star at the tip of the sword, called Hathisa, is even farther, a distant sun over 1,350 light-years from us. This simple asterism, a fixture of human mythology and navigation, is a pure accident of alignment. We are looking down a celestial tunnel where unrelated objects just happen to fall along the same line of sight. This realization transforms the sword from a connected object into a cosmic diorama, a layered display of depth. It means the brilliant Mesa is actually far behind the nebula, shining through it from a greater distance, while Hathisa sits even further back in the cosmic backdrop. Their light, traveling for centuries, arrives at our eyes in the same moment, weaving a flat picture from a deep reality. This illusion underscores a humbling truth about our view of the cosmos. The patterns we impose on the night sky, the gods and weapons and animals we have seen there for millennia, are often just temporary alignments, a trick of geometry played across unimaginable distances. Orion's sword is not a weapon but a keyhole, offering us a single, narrow sightline through the vast and mostly empty frontier of our galactic arm. These hidden magnetic fields guide the most violent and beautiful eruptions of all. Scattered throughout the Orion Nebula, often appearing as faint, glowing wisps or tiny, knotted bows of light, are objects designated with the initials HH. These are Herbig-Haro objects, and they are the cosmic birth cries of infant stars. Each one is a glowing shock front, a celestial sonic boom made visible. They are created by jets of material screaming away from the poles of a protostar, a star still in the process of forming. As this star gathers mass from its surrounding disk of gas and dust, it does not swallow everything. Some of the material, superheated and magnetically funneled, gets channeled and blasted outward at the star's north and south poles. These jets are narrow, focused beams of plasma traveling at speeds of several hundred kilometers per second, like cosmic fire hoses turned to maximum force. When these supersonic jets slam into the slower-moving gas of the surrounding interstellar cloud, they create a violent collision. The impact compresses and heats the gas to extreme temperatures, causing it to glow brightly across multiple wavelengths. This is what we see as an HH object. It is not the jet itself, but the brilliant, turbulent splash where the jet meets the resistance of the wider nebula. Within Orion, some of the most famous examples are HH1 and HH2, a spectacular pair located near the massive star-forming region. They look like 2 glowing, chaotic clouds facing each other, but they are actually the twin shock fronts from a single, powerful jet erupting from an unseen young star buried between them. The material is being shot out in opposite directions, plowing into the nebula on either side. These jets play a critical role in the star's development. By blasting away excess material and angular momentum, they act as a release valve, allowing the baby star to finally stabilize and stop spinning itself apart. They also clear out a cavity around the star, effectively cutting off its own food supply and determining its final mass. In a very real sense, these brilliant, destructive fountains are how a star sculpts its own future, carving out its space in the universe with furious, luminous precision. The brilliant jets of infant stars are not the only source of shifting light in this cosmic cloud. For centuries, astronomers gazing at the Orion Nebula have recorded something deeply puzzling. Its apparent brightness seemed to flicker across the decades. The great observer William Herschel, in the late 1700s, meticulously documented the nebula's form and declared it to be unchanging. Yet others, looking through their own telescopes in the years that followed, insisted the great cloud was growing fainter or perhaps even brighter. This sparked a long-standing debate: were these shifts genuine cosmic events or merely tricks of human perception and imperfect optics? For a long time, the consensus leaned toward illusion. Early telescopes suffered from limitations, with lenses and mirrors that produced different levels of contrast and clarity. Observers used different magnifications, and the very quality of a dark, steady night sky varied tremendously. The human eye itself is a subjective instrument, easily fooled by expectations and fatigue. It seemed likely that the nebula's variability was a story written not in starlight, but in the limitations of those trying to capture it. Modern astronomy, however, has revealed a more fascinating truth. While the nebula's overall glow is stable, specific regions within it do indeed pulse with real variability, and the cause is a dynamic interplay of light and shadow on an interstellar scale. One key mechanism involves the dense, dark clouds of dust that drift within the nebula itself. These are not static walls, but complex, roiling structures. As they move, even slightly, they cast vast, dark shadows across the background of glowing gas. From our fixed viewpoint, a drifting dust cloud can slowly eclipse a bright patch of nebula, causing that specific area to dim over months or years. Later, as the cloud moves on, the region brightens again. It is akin to a slow-motion cloud passing in front of the sun, changing the light on a landscape. But here the cloud is light years across, and the landscape is made of ionized hydrogen. The other source of change comes from the illuminating stars themselves, particularly the massive, volatile members of the trapezium cluster. These young stellar giants are prone to violent outbursts and fluctuations in their fierce ultraviolet output. A temporary increase in a star's activity can pump more energy into the surrounding gas, causing pockets of the nebula to flare in response. Conversely, a slight dimming in the star, perhaps due to a passing veil of its own ejected material, can cause a localized fading. So the historical observers were not entirely wrong. They were detecting a subtle, complex reality. The Orion Nebula is not a static painting, but a living diorama where dark dust clouds perform a silent celestial shadow play, and the central stars flicker like uncertain torch flames, together writing a slow, luminous story of change across the deep time of space. This slow celestial shadow play finds its grandest stage in the nebula's most prominent dark feature. Slashing into the brilliant heart of the Orion Nebula is a deep, in-sky intrusion known as the Dark Bay, a silhouette so sharp it looks like a piece of the void itself has been cut out of the glowing cloud. Its shape, curving and menacing, has also earned it the name the fish's mouth, as if some cosmic leviathan is about to swallow the trapezium stars, but this is no empty hole. The Dark Bay is a colossal mountain range of cold gas and dust, a dense molecular cloud situated directly between us and the nebula's luminous background. It is not a part of the nebula, but a foreground object, a separate, dark giant drifting through space and by pure chance aligning perfectly to block our view. Its material is so incredibly thick and cold that the fierce ultraviolet light from the trapezium cannot penetrate it to ionize the gas within, nor can visible light pass through to illuminate what lies behind. Instead, this dark mass acts as the ultimate cosmic stencil. The brilliant light from the nebula floods in from the sides and from behind, but wherever the dark bay's complex topography rises, it casts profound, detailed shadows onto the glowing gas far in the background. This is the secret behind the nebula's breathtaking texture and three-dimensional depth. Those delicate filaments, bright ridges, and deep cavities we admire are not just structures of glowing gas. They are also a masterpiece of light and shadow painted by this intervening dark cloud. Every contour of the dark bay's silhouette, every peak and valley in its dusty terrain, is mapped onto the nebula as a variation in brightness. A slight thinning in the cloud might allow a faint glow to seep through, creating a luminous rift, while a particularly dense knot casts a shadow so deep it appears as a void. This interplay gives the nebula its sculpted, almost tactile quality, making it look less like a flat painting and more like a cavernous, illuminated landscape. So the next time you see an image of Orion, remember that its most famous dark feature is not an absence but a presence. It is a monumental, light-absorbing sculpture, and the beautiful nebula behind it is the canvas upon which its immense, dark shadow is beautifully cast. That dark silhouette is a cosmic coincidence, a foreground mountain blocking our view, but another connection between Orion and Earth is far more direct, streaking across our atmosphere every year. Each October, the Orionid meteor shower paints the night sky with swift, bright trails, seeming to radiate from the constellation Orion itself. This annual light show creates a beautiful, though misleading, link in our minds. The source of these meteors is not the nebula, but one of the most famous visitors in human history, Halley's Comet. As this comet swings through the inner solar system on its 76-year orbit, the sun's heat boils away ice and dust, leaving a scattered stream of debris along its path. Every October, Earth plows directly through this river of ancient cometary grit. When those tiny particles, often no larger than a grain of sand, hit our atmosphere at tremendous speed, they vaporize in brilliant flashes, the shooting stars we call the Orionids. So the nebula is not the parent but merely the stunning backdrop. Yet this fact invites a much deeper cosmic question. If the meteors come from a comet, and comets are ancient, icy leftovers from the formation of our solar system, where did their raw materials originally come from? This is where the Orion Nebula re-enters the story, not as a direct source but as a prototype. Within its swirling cauldron, in the cold outer regions of protoplanetary disks around young stars, ices and dust grains are coalescing right now. These are the very seeds of future comets. The complex organic molecules forged in places like the hot core freeze onto dust grains in these frigid zones, building the dirty snowballs that will one day become cometary nuclei. In a very real sense, the nebula is a factory demonstrating the universal process that creates the building blocks of comets. The water in Halley's Comet, the carbon-based compounds in its dust, the very atoms in its structure, all were forged in the heart of ancient, massive stars that lived and died long before our sun was born. Those elements were then scattered into space, incorporated into a cloud like the Orion molecular cloud, and finally assembled into new solar systems. So while the Orionids do not come from the Orion Nebula, the nebula shows us where the recipe for all such comets and the meteors they spawn is written. It is a living example of the great cosmic recycling chain, where the death of one generation of stars provides the ingredients for the next, complete with the icy messengers that will one later rain light upon alien worlds. The same cosmic dust that sculpts shadows may be hiding a glittering secret. Deep within the Orion molecular cloud, radio telescopes have detected a faint, pervasive hum known as anomalous microwave emission. This is a specific kind of light, a low-energy radio glow that does not fit the profile of any known process. It is not the thermal warmth of dust grains, nor the synchrotron radiation from electrons spiraling in magnetic fields. It is something else entirely, a ghost signal with no obvious source. For years, this emission was a persistent, quiet mystery on the interstellar charts. Then a truly dazzling hypothesis emerged. The signal could be coming from the smallest diamonds in the universe. The theory proposes that mixed within the normal soot and silicate of interstellar dust are countless nanodiamonds, carbon crystals just a few billionths of a meter across. These are not gemstones forged in planetary pressures, but likely created in the cooling atmospheres of carbon-rich stars and then scattered into space. The key to their glow is spin. These tiny crystals are thought to carry an asymmetric electric charge. As they are buffeted by collisions with atoms and struck by photons of starlight, they are sent into a frantic, ultra-rapid rotation, spinning billions of times per second. A spinning charged object acts as a microscopic radio transmitter, and the collective hum from trillions upon trillions of these spinning nanodiamonds could, in theory, produce the exact anomalous microwave signal we detect. The evidence is intriguing but circumstantial. Spectral signatures hinting at carbon crystals have been found in other cosmic environments, and laboratory studies show that nanodiamonds can indeed spin at the required incredible rates. The hypothesis elegantly links two puzzles: the mysterious microwave glow and the known presence of certain carbon compounds, yet major questions spin right alongside them. If nanodiamonds are so common, why is this anomalous emission not detected more strongly everywhere? What specific conditions in Orion are making them spin so conspicuously? Competing theories suggest the emission could come from other vibrating organic molecules or from a particular kind of radiation process within the dust grains themselves. The idea of a cloud filled with spinning interstellar diamonds is a captivating one, a universe far more luxurious in its hidden details than we ever supposed. Whether this glittering theory holds its facet under further scrutiny remains to be seen, but it reminds us that the cosmos often reserves its most bizarre explanations for its quietest signals. Beyond the visible glow lies an entire hidden landscape painted in the warmth of infrared light. Here, three bizarre power sources dominate the scene, each a cryptic signature of violence and birth. The first is a turbulent knot known as the IRC-2 complex. This is not a single star, but a seething nest of activity buried so deep in the molecular cloud that no visible light escapes. At infrared wavelengths, however, it blazes as one of the brightest spots in the entire Orion region. This chaotic glow comes from a dense cluster of massive young stellar objects, suns so newborn they are still swaddled in thick, dusty cocoons. Their combined radiation, absorbed by the surrounding dust and re-emitted as heat, creates this brilliant but confused infrared smudge. It is a stellar maternity ward viewed only through the thermal imprint on the walls. Just a short cosmic distance away from this nest glows the enigmatic Nebula object. Unlike the extended smear of IRC-2, this appears as a sharp, brilliant point of infrared light. It is a beacon shining through a nearly opaque fog. Astronomers believe it is a single, incredibly massive star in the very final throes of its formation. It has cleared a small cavity around itself with its fierce radiation, but remains deeply embedded, its visible light completely extinguished by the remaining shroud of dust. We are essentially seeing the heat signature of a stellar titan moments before it emerges to dominate its surroundings. Then there is Source N, a third deeply embedded powerhouse whose true nature is still hotly debated. Some observations suggest it is similar to the Nebula object, another massive protostar. Other data hints it could be something even more extreme, perhaps a dense cluster of lower mass stars, or a region where powerful shockwaves from unseen outflows are violently heating the dust. Its ambiguity is a reminder that in this buried realm, even our most advanced infrared eyes can struggle to distinguish a single brilliant monster from a crowded riot of smaller, furious suns. Together, these three cryptic sources map a hidden geography of raw power, a triangle of infrared beacons where the nebula's most massive and influential stars are fighting their way out of the dark. These hidden infrared beacons are not the only structures fighting to emerge from the dust. The Hubble Space Telescope has revealed a different kind of struggle, one that etches violent, ephemeral shapes directly into the nebula's glowing face. Streaking outward from the dense core of the molecular cloud are bizarre, elongated structures that look for all the world like cosmic tornadoes. They are vast twisting columns of gas, some stretching over half a light year in length, with distinct spiraling patterns along their sides. They do not spin like terrestrial tornadoes, but their visual resemblance is uncanny and ominous. These are not funnels of descending air, however, they are the luminous wakes of destruction. The leading explanation points to the very bullets of gas we encountered earlier, the shrapnel from that ancient explosion in the Kleinman Low region. As these dense, massive knots of material are shot through the surrounding nebula at speeds exceeding 400 kilometers per second, they do not slip through cleanly. Instead, they act like celestial speedboats plowing through a calm sea. The knot's passage creates a powerful bow shock in front of it, compressing and heating the gas. But behind it, the story gets even more interesting. The turbulent flow of material streaming around the dense knot becomes unstable, breaking into swirling vortices that trail behind for astonishing distances. These vortices are the twisted columns we see. They are essentially the turbulent exhaust, the glowing, fossilized imprint of a supersonic journey. The intense ultraviolet light from the trapezium stars illuminates this chaotic aftermath, making the violent physics visible. Each tornado is a fossil record of motion, a snapshot of a knot's trajectory frozen in glowing gas. They can persist for thousands of years, long after the knot that created them has moved on or dissipated, serving as lingering signposts to past violence. This transforms our understanding of the nebula's landscape. What we might casually admire as beautiful, ethereal swirls is actually the scar tissue from a high-speed cosmic collision, a permanent bruise in the gas that tells a story of incredible force and momentum. It is a reminder that in this nursery, even the most graceful forms are born from violence. The violence of supersonic tornadoes marks one extreme of stellar birth, but the Orion complex holds quieter laboratories just as profound. Lying adjacent to the turbulent chaos of OMC1 is its comma sibling, the Orion Molecular Cloud 2. This filament is also dense, cold, and actively forming stars, yet it presents astronomers with a contrasting mystery. Here, the process seems more orderly, less explosive, a gentle simmer compared to OMC1's raging boil. While its famous neighbor is being shredded by the ancient bullet explosion and illuminated by the trapezium's fury, OMC2 exists in relative peace. It is further from the most massive, disruptive stars, allowing a different story to unfold. The stars being born here are predominantly smaller, sun-like stars rather than brilliant, short-lived giants. Their formation appears less violent, characterized by slower collapses and more modest outflows. This raises a fundamental question: why do two clouds, born from the same vast reservoir of material and separated by only a few light years, exhibit such different personalities? The answer may lie in the subtle architecture of the clouds themselves. Measurements suggest OMC2 might be slightly less dense overall than OMC1. This small difference in pressure could mean that the cloud cores within it collapse more gently, never reaching the critical thresholds needed to form the most massive, unstable stars whose births are inherently catastrophic. The alignment of magnetic fields may also play a decisive role. In OMC1, the fields are strong but may be more tangled, perhaps due to past shockwaves from nearby supernova or stellar winds. This turbulence can trigger rapid, chaotic collapse. In OMC2, the magnetic fields appear more uniform and orderly, acting as a stronger supporting skeleton that resists gravity's pull. slowing down the entire process and allowing material to accrue more gradually. Most tellingly, OMC2 shows no evidence of a recent, devastating event like the bullet explosion that still ripples through OMC1. That cataclysm likely scrambled the entire neighborhood, compressing some regions violently to ignite new stars while disrupting others. OMC2, sheltered from that specific shock, has been allowed to evolve under its own quieter rules. This makes it an invaluable control subject. By studying the calm, steady star formation in OMC2, astronomers gain a clearer baseline to understand what is normal, and then can better identify how the extraordinary violence in OMC1 alters the recipe. It demonstrates that the universe has multiple pathways to create stars, from catastrophic detonations to slow, persistent whispers, all occurring within the same stellar nursery. Those quieter pathways of star formation offer a stark contrast to a far more energetic phenomenon. The Orion Nebula complex is not just a birthplace for stars, it is a suspected particle accelerator on a galactic scale, a potential cosmic ray factory. Cosmic rays are not rays of light at all, but atomic nuclei stripped of their electrons, mostly protons, hurtling through space at nearly the speed of light. They carry unimaginable energy, millions of times more than particles in any human-made collider. For over a century, their origin has been one of astronomy's great mysteries, and the turbulent heart of Orion presents a compelling suspect. The recipe for creating such extreme particles requires a powerful engine and a relentless slingshot. Orion has both in abundance. Consider the supersonic stellar winds from stars like Theia to 1 Orionis C, screaming outward at thousands of kilometers per second. Picture the violent Herbig-Haro jets blasting from infant stars and slamming into nebula gas. Recall the ancient bullet explosion in the Kleinman Low region, whose shockwaves still ripple through the cloud. Each of these events creates a powerful, moving shock front, a sudden, drastic change in pressure and velocity in the surrounding gas. These shock fronts are nature's perfect particle accelerators. When a stray proton or atomic nucleus gets caught in the path of one of these advancing shock waves, it can be reflected back and forth by magnetic fields trapped within the shock, gaining a tremendous speed boost with each crossing. Over time, this process, called diffusive shock acceleration, can whip particles up to a significant fraction of light speed, turning them into the cosmic rays that eventually escape into interstellar space. We have compelling, though indirect, evidence this is happening in Orion. High above Earth's atmosphere, space telescopes have detected a distinct glow of high-energy gamma rays emanating from the Orion molecular cloud. Gamma rays are the most energetic form of light, and in this context they are a crucial clue. They are believed to be produced when these freshly minted, ultra-fast cosmic ray protons collide with the nuclei of slower-moving atoms in the dense cloud. The violent impact generates a cascade of particles and energy, ultimately releasing a gamma-ray photon. This telltale signature strongly suggests that the nebula's ongoing turmoil is actively manufacturing these elusive, high-speed particles. While supernova remnants are often cited as the primary cosmic ray factories, regions of intense, clustered star formation like Orion present a compelling parallel. It means the chaotic birth cries of stars may be responsible for seeding our galaxy with a constant, invisible rain of atomic shrapnel, a high-energy byproduct of creation that quietly permeates the void. This invisible rain of atomic particles is born from the same fundamental stuff that veils the nebula's light. The dark lanes and shadows we see are not empty voids, but clouds of interstellar dust, a fine cosmic powder that permeates the space between the stars. But to call it simple soot would be a profound misunderstanding. The dust in the Orion Nebula is a complex, engineered material, a testament to the intricate chemistry of stellar death and rebirth. When astronomers point their spectrometers at the nebula, they are not just measuring light, they are taking the chemical fingerprint of these tiny grains. The light absorbed and re-emitted by the dust reveals a precise mineralogical catalogue. A significant portion is made of silicates, the same family of minerals that form the bulk of Earth's rocky crust. Within this silicate family, a specific crystal called forsterite has been definitively identified. Forsterite is a magnesium-rich silicate, a primary component of the gemstone peridot and of the rock dunite in Earth's mantle. Finding it floating freely in space is astonishing. It tells us that the extreme temperatures and pressures found deep within planets can also occur in the cooling outflows of dying stars or in the violent shocks between colliding gas clouds. These crystals condense directly from a vapor of silicon, magnesium, and oxygen, growing in the expanding envelopes of aging giants before being blasted into the interstellar medium. Alongside the silicates is another major component, carbonaceous material. This is not pure graphite or diamond, but a messy, complex amalgam often referred to as amorphous carbon, laced with hydrogen and other atoms. It is more like the char from a fire than a precise crystal. In the frigid outer reaches of the nebula, far from the trapezium's heat, these silicate and carbon grains become coated in a mantle of ice. Not just water ice, but ices of carbon monoxide, carbon dioxide, methane, and ammonia, creating tiny, frozen, dirty snowballs. What makes Orion's dust particularly unusual is the specific balance and processing of these ingredients. The fierce ultraviolet radiation from the hot young stars acts like a cosmic tanning lamp, aggressively processing the dust grains. It can blast away the icy mantles, strip hydrogen atoms from the carbonaceous material, and even damage the crystalline structure of the silicates, turning ordered crystals into a more glassy, amorphous state. This means the dust we see in the brilliant central cavity is weathered and altered, while the dust in the cold, dark molecular cloud behind it remains pristine and icy. By comparing the dust here to that in quieter, older regions of space, astronomers see a clear difference. Orion's dust is younger, more recently forged, and actively being transformed by its violent environment. Each microscopic grain is a time capsule and a laboratory, a piece of cosmic sediment recording the very conditions that now seek to destroy it. These microscopic grains of cosmic dust are the raw material for new solar systems, yet the final products of Orion's stellar factory present a curious statistical puzzle. For every brilliant, massive star like those in the trapezium, astronomers expect to find a vast crowd of smaller, fainter siblings. This predicted distribution of stellar sizes is called the initial mass function. It is a fundamental rule of cosmic demography, suggesting that for every star 10 times the mass of our Sun, there should be hundreds of stars with the mass of our Sun or less. In most star-forming regions we observe, this rule holds true. The universe seems to have a strong preference for manufacturing humble red dwarfs over brilliant blue giants. But in the Orion Nebula cluster, the numbers are not adding up. The census of low-mass stars appears surprisingly sparse. Where is the expected multitude of faint, diminutive suns? One compelling theory points directly to the nebula's famous veil of dust. Could these legions of red dwarfs simply be hiding? The dense molecular cloud from which the cluster formed, and the dusty remnants still swirling within it, are exceptionally effective at dimming starlight. A faint, cool star buried behind even a modest curtain of this dust could be rendered completely invisible to our optical telescopes. It is like trying to count people in a dense fog. You will easily spot those carrying bright lanterns, but anyone with a faint candle might be completely obscured. Surveys using infrared telescopes, which can peer through the dust, have indeed found more low-mass candidates, but the counts still seem lower than the universal rule would predict. This leads to a second, more dynamic possibility: ejection. The Orion Nebula cluster is a crowded, violent neighborhood. The gravitational interactions between young stars, especially in their dense birthplace, can be chaotic and fierce. Computer simulations show that close encounters between stellar siblings can act like a cosmic slingshot. A lower mass star, being more easily bullied by the gravity of its more massive neighbors, can be flung out of the cluster entirely at high speed, destined to wander the galaxy alone as a runaway star. Over the first few million years of the cluster's life, hundreds of such faint stars could have been evicted, scattering into the dark before we ever got a chance to count them. A third, more profound idea challenges our understanding of the star formation recipe itself. Perhaps the conditions in the Orion molecular cloud were special. Maybe the cloud was unusually warm, or its magnetic fields were particularly strong, or the turbulence within it was exceptionally fierce. Any of these factors could have shifted the fragmentation process, causing the cloud to break apart into larger, denser clumps that naturally collapsed into more massive stars, skipping the production of countless smaller ones. In other words, the initial mass function might not be a universal constant, but a variable that depends on the specific environment. This missing stars mystery is more than a head count. It is a direct test of our theories about how stars are born. Are the faint multitudes truly absent, or are they just lost in the glare and the gloom? The answer will tell us if Orion is an exception to a cosmic rule, or if the rule itself needs rewriting. This search for missing stars forces us to step back far beyond the nebula's glowing heart, to see the entire Orion complex as a single, breathing entity. From this grand perspective, the most dominant features are not delicate filaments or dark bays, but colossal cavities, vast bubbles blown into the fabric of the galaxy itself. These are not the work of a single star, but the cumulative legacy of generations of stellar giants. For millions of years, the massive stars born within Orion have lived fast and died young. During their brief lives, their ferocious winds act like cosmic blowtorches, carving out hollows in the surrounding gas. When these stars inevitably explode as supernova, the blasts inject titanic amounts of energy, pushing outward with unimaginable force. Each supernova shockwave sweeps up the surrounding material, including the previously blown wind bubbles, piling it into a dense, expanding shell. Over eons, this cycle repeats, with new generations of massive stars forming in the compressed walls of older bubbles, only to then explode and create new ones. The result is a nested, chaotic structure of superbubbles within the Orion arm of our galaxy, some spanning hundreds of light years across. These bubbles are the primary architects of the interstellar medium on a galactic scale. They redistribute matter, mixing the heavy elements forged in stellar cores throughout the cloud. They regulate the very cycle of star formation itself, by both triggering new births in their compressed shells and also, ultimately, by shredding the molecular cloud that birthed them, bringing the stellar nursery era to a close. This grand, cyclical process may hold a deeply personal clue to our own origins. There is compelling evidence that our solar system, over 4.5 billion years ago, was born in the aftermath of a similar nearby superbubble. Specific isotopic signatures found in ancient meteorites, rare forms of elements like iron-60, point to the debris from a nearby supernova or a cluster of them being injected directly into our primordial solar nebula as it was coalescing. This suggests our Sun and its planets did not form in an isolated, quiet cloud, but rather in a region energized and enriched by the death of massive stars, perhaps on the turbulent edge of a giant bubble, not unlike those we see being forged in Orion today. We may, in fact, be the children of a cosmic cavity, our entire existence a direct product of the same violent, creative forces that are now, right before our eyes, sculpting the nebula in Orion's sword. This grand, cyclical process of stellar birth and death does not confine itself to the nebula's immediate borders. Its influence expands across the heavens, connecting Orion to a constellation far across the winter sky. Stretching from the Hunter's Shoulder deep into the river of Eridanus lies one of the largest structures in our galactic neighborhood, the Orion Eridanus superbubble. This is a titanic cavity in the interstellar medium, a roughly spherical void over 1,000 light-years wide, with its interior filled with million-degree gas so thin it is a better vacuum than any we can create on Earth. Its walls are wispy filaments of cooler gas, glowing faintly in soft X-rays and ultraviolet light, tracing the outline of a colossal cosmic bubble. The Orion Nebula itself sits like a brilliant jewel on the bubble's near edge, a single, intensely active knot in a far vaster tapestry. The creation of such an immense void required a power source beyond any single star. Astronomers reconstruct a history of sustained violence. Over the past 10 to 20 million years, multiple generations of massive stars were born in the giant molecular clouds that once filled this region. These stars, living fast and dying young, did not go quietly. One by one, they ended their lives as supernova, their cataclysmic explosions pumping unimaginable energy into the surrounding space. Each blast wave expanded, sweeping up gas and merging with the remnants of previous explosions, collectively pushing and heating the interstellar material into the expanding shell we see today. It is the fossilized remnant of a stellar war zone, a monument to the collective death cries of perhaps dozens of stellar giants. This superbubble is not a relic, it is an active shaper of our local galactic environment. Our own solar system, traveling through the galaxy, is currently located inside this very structure, or perhaps just skimming its boundary. The hot, thin plasma within the bubble surrounds us, influencing the density and pressure of the space through which our sun moves. This environment affects how cosmic rays propagate and how the solar wind interacts with the interstellar medium at the very edge of our heliosphere. We are, in a very literal sense, living inside the aftermath of Orion's ancient violence. The nebula's brilliant glow is not an isolated spectacle, but the brightest flare from an ongoing geological process on a galactic scale, a process whose consequences we are floating within right now. That superbubble's million-degree interior points directly to a hidden layer of the nebula itself. If we could see the sky with X-ray eyes, the serene glow of Orion's cloud would vanish, replaced by a furious, crackling landscape of pure energy. The Chandra X-ray Observatory has revealed the Orion Nebula not as a placid pond of gas, but as a seething cauldron of plasma heated to temperatures beyond 1,000,000 degrees Celsius. This diffuse, high-energy glow permeates the entire region, a thin, superheated fog woven between the cooler, visible filaments. The source of this incredible heat is not a quiet simmer, but a continuous barrage of cosmic violence. Remember those supersonic stellar winds screaming from stars like they, the one Orionists see at thousands of kilometers per second. When these gales slam into the surrounding nebula gas or collide with each other, they create powerful shock waves. Think of the sonic boom from a jet, but magnified to a stellar scale and happening constantly. These shock waves compress and heat the gas to extreme temperatures, transforming it into the diffuse X-ray emitting plasma that fills the cavities and bubbles. It is the thermal echo of the nebula's relentless stellar hurricanes, but the biggest surprise from the X-ray data was not this background fury. It was the discovery of thousands of pinpoint sources, individual stars shining brightly in X-ray light. Most startling of all, many of these are not the massive, hot trapezium stars, but their very young, low-mass sibling stars similar to our infant sun. These toddler stars should, by all classical reasoning, be relatively calm. Yet their X-ray output is staggering, often hundreds of thousands of times more powerful than the X-rays emitted by our present-day, middle-aged sun. The reason lies in the chaotic dynamo of a young star's interior. A star like our sun generates its magnetic field through the churning motion of its hot, electrically charged plasma, a process called a dynamo. In a newborn star, this engine is operating at a fever pitch. The star is spinning rapidly, and its interior convection is violent and turbulent. This supercharges the magnetic field, twisting and braiding it into complex, stressed knots. These magnetic loops can snap in enormous stellar flares, events that make solar flares look like mere sparklers. The coronae, the outer atmospheres of these young stars, are riddled with these magnetic explosions, heating them to tens of millions of degrees and causing them to blaze in X-rays. This intense magnetic activity has profound consequences for any potential planets forming in the system. The fierce X-ray and ultraviolet radiation can strip atmospheres from young worlds and aggressively bombard their surfaces. Yet, it might also provide the energy needed to drive chemical reactions on dust grains, potentially aiding the formation of prebiotic molecules. So the X-ray glow of Orion is a dual signature, a diffuse fog from the collective violence of stellar winds, and a sparkling constellation of individual magnetic tantrums from infant suns, each a beacon marking the turbulent childhood of a potential solar system. The violent X-ray glow of young stars is just one layer of the nebula's hidden energy. To hear its deeper voice, we must listen to the sky with a different kind of ear, one tuned to the long, silent waves of radio light. When radio telescopes like the Very Large Array turn their immense dishes toward Orion, the familiar glowing cloud vanishes, replaced by a ghostly web of intricate filaments and delicate wisps. This is the nebula's radio whisper, a map of its ionized gas and the magnetic fields that shape it. Unlike the broad brushstrokes of visible light, which show us where starlight illuminates gas, the radio view traces the gas itself, specifically the free electrons zipping through the hot, ionized plasma. Every twist and tendril in this radio map is a direct imprint of physics, revealing structures often completely invisible to optical or infrared eyes. Some of the most prominent radio wisps trace the edges of the great cavities blown by stellar winds, marking the shock fronts where million-degree plasma meets cooler gas. Others form intricate loops and arcs that align perfectly with the magnetic fields mapped by the veil, showing how those invisible lines of force sculpt and contain the nebula's expansion. The contrast is profound. An optical image shows the nebula's beauty, a luminous landscape of light and shadow. An infrared image reveals the hidden heat of embedded stars and warm dust. But the radio map strips away the decoration to show the skeleton and the sinew, the ionized bloodstream and the magnetic nervous system of the entire complex. It reveals a level of fine, filamentary detail that suggests constant, subtle agitation, as if the entire region is crisscrossed by the fading ripples from countless small shocks and turbulent eddies. These radio wisps are not static, they are a dynamic signature, a live readout of the energetic processes continuously churning within the nebula. They remind us that this stellar nursery is not a place of serene birth, but of constant electromagnetic turmoil, its true structure written in a language of radio waves that only our most powerful instruments can finally translate. These radio whispers are the calm afterglow of violence, but in specific, dense knots of the nebula, the gas itself begins to sing with a focused, unnatural brilliance. Deep within the shrouded cores of the Orion molecular cloud, natural cosmic lasers are firing, known as masers, an acronym for microwave amplification by stimulated emission of radiation. These are not machines but intense, coherent beams of microwave light generated by excited molecules in space. Imagine the difference between the warm, scattered glow of a city seen from afar and the piercing, focused beam of a lighthouse. A maser is that lighthouse, its light organized and amplified to stunning intensity by the unique physics of a cosmic cloud. The most common and powerful of these in Orion is the water maser. It occurs in regions of dense, warm gas that are being violently agitated, often right at the heart of the powerful jets screaming from newborn stars. Here, water molecules are not floating passively. They are pumped full of energy by collisions or radiation, elevating them to a high-energy state. When a passing microwave photon of just the right frequency strikes one of these excited molecules, it triggers a chain reaction. The molecule drops to a lower energy, releasing an identical photon, which then goes on to strike another excited molecule, creating two identical photons, and so on. This stimulated emission creates an avalanche of perfectly aligned microwave light, beaming out in specific, narrow directions. In Orion, intense water mazes act like brilliant strobe lights flashing from within the chaos of stellar outflows, marking the precise locations where supersonic jets are plowing into surrounding gas with tremendous force. They are the luminous signposts of shock and excitement on a molecular scale. While water mazes mark general turmoil, another type pinpoints a very specific and rare event. Methanol mazes are among the strongest known, and they are considered almost exclusive markers of high-mass star formation. These do not flare from just anywhere. They appear in the dense, dusty disks and toruses of gas that swirl around massive stellar embryos, objects still too hidden to see directly with telescopes. The methanol molecule, a simple alcohol, becomes excited in these unique environments, where temperatures and densities are perfectly tuned to pump its energy levels. When it begins to maser, it creates a brilliant, coherent beacon that screams through the dust. For astronomers, detecting a methanol maser is like finding a under-construction sign blinking in the depths of a dark cloud. It tells them that right here, at this exact spot, a massive star, a sun many times heavier than our own, is in the final stages of assembly, its gravity drawing in material from a vast disk that the maser illuminates from within. These natural lasers cut through the obscuring fog, providing our clearest guide to the hidden cradles of the nebula's future giants, where the ordinary rules of light are bent into beams of impossible clarity. These natural lasers pinpoint the violent birthplaces of massive stars, but to understand the nebula's future, we must track the paths of its existing inhabitants. Astrometric studies have now mapped the precise motions of thousands of stars within the Orion Nebula cluster, a painstaking effort to trace their individual journeys across the sky. The results are deeply puzzling. If the cluster were a simple, expanding family born from a single cloud, we would expect the stars to drift apart in a relatively orderly fashion, like fragments from a gentle explosion. That is not what the data shows. Instead, the stellar motions are chaotic and complex. While many stars follow the broad outward drift, others streak across this flow on strange, oblique angles. Some even seem to be moving in ways that suggest they are falling back inward or on looping, unpredictable paths. This proper motion puzzle reveals a history written in gravitational violence. Those stars on wild, anomalous trajectories are likely the survivors of close encounters, stellar slingshots that flung them off their expected courses millions of years ago. In the dense, young cluster, stars would have passed perilously close to one another, their immense gravity acting as a chaotic accelerator. A lower mass star venturing too near a more massive sibling could have been whipped into a new, high-speed trajectory, perhaps even ejected from the cluster entirely to become a runaway star drifting alone through the galaxy. These stellar speedsters, their origins forgotten, would leave behind only the subtle, skewed motions of the stars they interacted with. But gravitational interactions between visible stars may not explain all the anomalies. The strange paths of some stars could also be the subtle tug of unseen mass, the same hidden material hinted at by the cluster's missing gravity. Perhaps vast, dark reservoirs of cold gas, or a populous swarm of faint brown dwarfs and rogue planets, are gravitationally nudging the visible stars, warping their motions in ways we are only beginning to detect. Each anomalous trajectory is a clue to a past event, a silent witness to the rough and tumble environment of the nursery. This proper motion chaos confirms that the Orion Nebula cluster is not a serene birthplace, but a dynamic and often ruthless arena, where stellar destinies are forged and altered by close brushes with neighbors both seen and unseen. This chaotic stellar ballet unfolds within a nebula whose true shape has long been a mystery of light and shadow. While the visible glow shows us a flat painting, the nebula conceals its depth in a subtle ultraviolet game of hide and seek. The blistering radiation from the trapezium stars does far more than make the gas glow. It also casts profound, invisible shadows. This happens because the ultraviolet light that ionizes hydrogen, the very process that creates the nebula's famous red glow, can be completely blocked. When a dense, cold cloud of neutral atomic hydrogen drifts between the trapezium and a more distant section of the nebula, it acts like a cosmic curtain. That specific cloud absorbs the critical ultraviolet photons that would otherwise ionize the hydrogen behind it. From our perspective, this creates a dark patch in the nebula's ultraviolet emission, a shadow in the light we cannot see with our eyes. But to astronomers using space telescopes sensitive to ultraviolet spectral lines, these shadows are as clear as silhouettes on a screen. They are not shadows of darkness, but shadows of inactivity, regions where the energetic process of ionization has been temporarily paused by an intervening obstacle. This simple principle becomes a powerful tool for cosmic cartography. By carefully mapping which parts of the nebula are glowing in ionized hydrogen and which are dark in the specific ultraviolet light that causes that ionization, scientists can work backward. They can trace lines of sight from the trapezium, the known light source, out into the cloud. A shadow tells them that along that particular line, there must be a dense knot of cold hydrogen blocking the path. More importantly, by comparing multiple shadows and their relationships, astronomers can begin to assemble a three-dimensional model. If a shadow appears in front of a known bright filament, that shadow-casting cloud must be closer to us than the filament. If another shadow seems to lie behind a different glowing structure, then that cloud is deeper in the nebula. Piece by piece, shadow by shadow, they build a topological map of the entire region. This ultraviolet shadowing reveals that the Orion Nebula is not a simple, hollow shell lit from within. It is a complex, folded landscape of glowing walls, dark pillars, and isolated clouds, all arranged at different distances from the central stars. Some of the dark features we see in visible light, like the dark bay, are confirmed to be in the foreground, but others, hidden from optical view, are revealed by this technique to be deep in the background, perhaps even on the far side of the cavity. It is a method of seeing depth where our eyes see only a flat canvas, using the absence of a specific kind of light to reveal the solid structures of an invisible world. Those ultraviolet shadows map a complex landscape, but within the very atoms of the nebula's youngest stars lies a subtle chemical mystery that defies our models. Astronomers call it the lithium problem. Lithium is one of the three lightest elements forged in the Big Bang, a fragile atom easily destroyed in the hot cores of stars. For Sun-like stars, this destruction is a reliable clock. As a low-mass star contracts and heats up during its infancy, the temperature at its core quickly becomes hot enough to begin fusing lithium. This process consumes the element at a predictable rate, so by measuring how much lithium remains in a star's atmosphere, we can essentially take its temperature and estimate its age. The less lithium, the older and more evolved the star should be. This works beautifully for stars in most clusters, but in the Orion Nebula cluster, the clock appears broken. Spectroscopic studies of many young, low-mass stars here reveal a puzzling spread. While some show the expected, heavily depleted lithium levels consistent with their estimated million-year age, others shine with a surprising abundance of the element, as if their internal furnaces have not yet fully ignited. These stars seem, chemically speaking, too young for the neighborhood. One compelling explanation is that they simply are younger. The Orion complex did not form all its stars in a single, brief burst. If star formation here occurred in multiple waves over several million years, as the age spread in the trapezium also suggests, then we would expect to find stars of different ages mixed together. The lithium-rich stars could be true latecomers, stellar infants just a few 100,000 years old, whose cores have not yet reached the critical temperature to burn lithium efficiently. They would be the younger siblings in a family portrait that includes much older brothers and sisters. Another fascinating possibility involves not the star's age, but its diet. These stars are all surrounded by, or were recently surrounded by, thick protoplanetary disks. That disk material is cold and pristine, having never been subjected to the star's internal heat. It contains the full, primordial abundance of lithium from the original molecular cloud. If a young star accretes or pulls in a large amount of this fresh, lithium-rich gas from its disk after its initial contraction phase, it could be replenishing its atmospheric lithium faster than its core can burn it. Imagine a runner trying to lose weight while also being fed a steady stream of cake. The net effect could be a stable, higher weight despite the exercise. This accretion could happen in bursts during episodes of heightened disk activity, temporarily painting the star's surface with a youthful chemical signature. There is also a more exotic third idea that the internal structure of these particular stars is different. Perhaps stronger magnetic fields or faster rotation are inhibiting the mixing of material between the surface and the core, trapping lithium in the cooler outer layers where it can survive. Each explanation points to a more dynamic and varied childhood for stars than our standard models allow. The lithium problem is a quiet but persistent clue, written in the faint spectral lines of a lightweight element, suggesting that the path from a collapsing cloud to a stable sun is messier, more prolonged, and more individual than we ever guessed. The fragile lithium in a star's atmosphere is one clock, but the distance to the nebula itself is the most fundamental measurement of all. The Orion Nebula is not just a beautiful spectacle, it is a cornerstone of cosmic cartography, a critical anchor point in our quest to map the scale of the universe. This glowing cloud, sitting roughly 1,344 light-years away, serves as a crucial rung on what astronomers call the cosmic distance ladder. This ladder is a series of overlapping techniques, each building upon the previous, that allows us to measure the mind-boggling distances from our solar system to the farthest galaxies. Think of it like this: you cannot measure the width of a continent with a single ruler. You need a chain of tools, starting with a tape measure for your backyard, then a surveyor's transit for a city, and finally satellite triangulation for the continent itself. The cosmic distance ladder works the same way. The first rung, the tape measure of space, is stellar parallax. This is a simple geometric method based on the apparent shift of a nearby star against the background of much more distant stars as Earth orbits the Sun. It is like holding your thumb out and closing one eye, then the other. Your thumb appears to jump back and forth. The size of that jump tells you how far away your thumb is. For the Orion Nebula, the European Space Agency's Gaia mission has performed this stellar survey with breathtaking precision, measuring the minuscule parallax wobble of the trapezium stars themselves. This gives us a direct geometric distance to the nebula's heart, a measurement with an uncertainty of less than 1%. This precise, anchored distance is the gift that keeps on giving. Because we know exactly how far away the Orion Nebula is, we can calibrate other secondary distance indicators that work for objects much farther away. For example, by studying the brightness and types of stars within the nebula's well-understood cluster, astronomers can establish a standard for what certain kinds of stars should look like when they are exactly 1,344 light-years distant. Then, when they spot a similar star in a distant, fuzzy galaxy, they can compare its apparent faintness to the Orion standard. Since light fades with distance according to a strict mathematical law, the difference in brightness reveals exactly how much farther away that galaxy must be. Orion's measured distance also helps calibrate pulsating stars called Cepheid variables, which are used as mileposts for neighboring galaxies, and even refines our understanding of supernova explosions, the brilliant beacons that light up the far reaches of the cosmos. Without a solid, nearby rung like Orion, the entire ladder would wobble, and every measurement of the expanding universe, its age and its fate, would be built on uncertain ground. So when you look at that fuzzy patch in Orion's sword, you are not just seeing a cloud of gas, you are looking at a fundamental benchmark, a celestial survey marker from which we measure the depth and grandeur of everything else. That cosmic distance ladder is built upon a stable present, but the very ground beneath our feet holds evidence of a violent past. The Orion Nebula's brilliant activity is not an isolated event, but part of a chain of cosmic explosions that may have directly touched our world. Scattered across the ocean floor and embedded deep within Antarctic ice, scientists have discovered a rare radioactive isotope called Iron-60. This form of iron is not native to Earth. It is forged only in the furious hearts of massive stars and scattered into space during their supernova deaths. The presence of these atoms in sediment layers dated to roughly 2.5 million years ago is a smoking gun. A nearby star exploded and its elemental shrapnel rained down on our planet. The prime suspect for this cosmic neighbor lies in the direction of the Orion complex. While pinpointing the exact culprit star is challenging, as the expanding debris cloud has since moved on, the Orion Arm is a region ripe with the kind of massive, short-lived stars that end as supernova. The structure of the local superbubble we inhabit, that vast cavity of hot gas, is itself the fossilized remnant of multiple such explosions over the last 10 to 20 million years. This suggests our solar system has been drifting through the aftermath of a stellar battlefield, a region sculpted by successive blasts. So the question becomes, is the Orion Nebula we see today the aftermath of such an event or the precursor to the next one? The evidence points compellingly in both directions. The nebula could very well be the expanding wreckage from a supernova that helped trigger the current wave of star formation. A blast wave from an ancient, now vanished star could have compressed the molecular cloud, initiating the collapse that led to the trapezium cluster and its brilliant siblings. The supersonic bullets and twisted tornadoes we see might be the lingering chaos from that detonation. Conversely, the nebula is also undoubtedly a factory for future supernova. The most massive stars in the trapezium, like Theta 1 Orionis C, are destined to live for only a few million years before they too explode. Their eventual deaths are written into their brilliant, furious natures. In a cosmic sense, we are watching both the product of past violence and the assembly line for future cataclysms. The Iron-60 in our seabeds is a tangible, physical connection to this cycle, a radioactive whisper that the serene night sky is a mask over an ongoing story of stellar life and death. A story in which our own world has occasionally played the role of silent witness, collecting the atomic dust from a star's final breath. That radioactive whisper from a supernova becomes a tangible grain of sand in our own cosmic backyard. Scattered throughout the most primitive meteorites, the unaltered building blocks of our solar system, are microscopic diamonds in the rough far more precious than gems. These are pre-solar grains, specks of stardust older than the sun itself. Each one is a literal time capsule, a piece of solid matter that condensed in the cooling atmosphere of a dying star billions of years ago, survived the violent dispersal of a supernova or stellar wind, drifted through interstellar space, and was finally captured by the swirling cloud that became our solar system. They are not from here, they are alien visitors, and their atomic passports tell a story written in isotopes. Isotopes are different forms of the same element, atoms that have the same number of protons but a different number of neutrons in their nucleus. The precise ratio of one isotope to another, like carbon-12 to carbon-13, acts as a forensic signature. It records the exact nuclear conditions where that atom was forged. Was it the steady burn of a low-mass star's core, the explosive helium flash of a red giant, the furious neutron capture of a supernova? Each stellar process leaves a distinct isotopic fingerprint. When scientists analyze these pre-solar grains with incredibly sensitive instruments, they find fingerprints that point directly to specific types of stars. Some grains carry the signature of classical nova, others of red giants. but a significant number bear the mark of massive, short-lived stars, the kind that dominate regions like the Orion Nebula today. These grains are rich in certain isotopes of oxygen, aluminum, and calcium that are overproduced in the violent nuclear reactions and strong stellar winds of hot, massive stars. This is where the connection clicks into place. Right now, in Orion, stars like Thay to 1 Orionis C are blowing fierce winds, ejecting not just gas but also solid particles into space. In these outflows, as the gas expands and cools, atoms collide and stick together, forming microscopic dust grains, tiny specks of sapphire, graphite, and silicon carbide. These newly formed grains are then blasted into the surrounding nebula and the wider interstellar medium, carrying with them the unique isotopic signature of their massive, brilliant parent star. Billions of years ago, in a different spiral arm of our galaxy, a similar drama played out. A massive star in a nebula much like Orion lived its fast life and died, seeding the local cloud with its wind-borne dust. That cloud eventually collapsed to form our Sun and its planets, and those ancient, resilient grains were incorporated intact. So when we hold a piece of a primitive meteorite, we are literally holding material that was forged in the heart and blown from the surface of a long-dead stellar giant. Parts of the Earth, of you and me, are made of atoms that once journeyed through a nebula just as turbulent and brilliant as the one we see in Orion's sword. The nebula is not just a distant spectacle, it is a working model of the cosmic factory that supplied the raw materials for our very existence. Every element heavier than hydrogen and helium in our bodies was made in a star, and some of those atoms took their final solid form in winds and explosions echoing the violence we witness in Orion today. The atomic history within us raises a profound question about our own perception of this cosmic forge. When you finally see the Orion Nebula through a telescope eyepiece, the view may surprise you. Instead of the vibrant greens and reds of famous photographs, you are more likely to see a soft, ethereal glow of grayish pink, perhaps with a hint of pale green. This difference between the camera's eye and our own is not an illusion, but a fascinating collision of astrophysics and human biology. The nebula's true light is dominated by two specific colors emitted by its excited gases. The most intense emission comes from hydrogen, the primary fuel of the nebula. When its atoms are energized by starlight and then calmed down, they release a very specific shade of deep red light known to astronomers as hydrogen alpha. The second strongest glow comes from oxygen atoms that have lost 2 electrons, a state called doubly ionized oxygen. These atoms emit a sharp, bluish-green light. To a camera sensor which collects light patiently over minutes or hours, these two colors combine. The camera's digital eye blends the strong red and the strong green, and with a little processing, we get those breathtaking portraits of salmon pink clouds and turquoise curtains. But our biological eyes operate under severe constraints in the darkness of a telescope view. In very low light, our vision switches from color-sensitive cone cells to monochrome rod cells, a state called scotopic vision. Our rods are most sensitive to blue-green light, but they cannot perceive color at all. So the delicate green glow from the oxygen is what primarily stimulates our rod cells, creating the overall impression of brightness but in shades of gray. The red hydrogen light, however, falls in a part of the spectrum where our dark-adapted rods are almost blind. That rich crimson is simply too faint for our night vision to register effectively. The faint hint of pink some observers report is a trick of a different sort, a phenomenon called photopic intrusion. It occurs when a small part of our color vision, perhaps from the brighter core of the nebula, briefly kicks in and blends with the rod signal, allowing our brain to interpret a slight reddish tone. So the majestic, colorful nebula of the posters is a kind of cosmic truth revealed through technology, while the subtle, ghostly wash of light in the eyepiece is an intimate, personal experience, a whisper of the nebula's glory filtered through the ancient, biological hardware of our own evolution. It is a reminder that the universe speaks in a full spectrum of information, but we are only ever hearing a single, beautiful note of the song. Our biological eyes capture only a whisper of the nebula's true story, but to understand its grand narrative, we must step into a universe built from pure mathematics. The Orion Nebula has become a critical proving ground not just for telescopes, but for the most powerful supercomputers on Earth. Inside these vast digital engines, astrophysicists are constructing entire simulated universes, digital twins of Orion designed to unravel the physics that telescopes can only glimpse. They begin with the fundamental ingredients, feeding in the precise measurements we have gathered: the density of the molecular cloud, the searing temperature of the trapezium stars, the ferocious pressure of their stellar winds, and the subtle pull of magnetic fields mapped from the veil. These numbers become the initial conditions for a cosmic experiment run in silicon. The simulation then unleashes the laws of physics, calculating the gravitational collapse of gas clumps, the hydrodynamics of shockwaves from stellar winds, the radiative transfer of blistering ultraviolet light, and the complex feedback as newly formed stars in turn influence their own birth environment. Watching these simulations unfold is like fast-forwarding through millions of years of cosmic history in a matter of days. You witness the molecular cloud begin to fragment, not randomly, but along the filaments dictated by magnetic fields and turbulence. You see protostars ignite within dense knots, their fierce radiation beginning to push back against the infalling gas. Cavities blow open, pillars of dense gas are sculpted by the erosive light, and jets of material scream from the poles of infant suns, carving paths through the digital nebula. The ultimate test comes when the scientists freeze their simulation and compare its snapshot to the real, observed nebula. Does the digital twin produce the sharp, glowing edge of the Orion bar in the right place? Does it generate the correct number and distribution of proplyds, those evaporating protoplanetary disks? Do the simulated stellar winds carve out cavities that match the shapes and sizes we see through our telescopes? When the simulation matches reality, it is a powerful validation that our underlying theories about gravity, radiation, and magnetodynamics are correct. But more often, there is a mismatch, and these discrepancies are where the true breakthroughs happen. Perhaps the simulated pillars of gas evaporate too quickly, suggesting our models for how radiation eats away at dust are incomplete. Maybe the stars formed in the simulation are not the right masses, hinting that some hidden process, like the chaotic interactions of disks around binary stars, is crucial. Each failure forces scientists to refine their code, add new physics, and question their assumptions, driving our understanding of star formation to deeper levels. These simulated universes are more than just pretty animations. They are rigorous laboratories where we can run the experiment of Orion's birth over and over, tweaking the parameters of reality itself to see which recipe truly builds the cosmos we see outside our window. These digital laboratories show us the potential for entire solar systems to be born, but what future awaits the hundreds of protoplanetary disks we see right now, those fragile proplyds glowing in the heart of the storm? Each one is a potential cradle for new worlds, but the environment here is a brutal test. The same ultraviolet radiation that makes the nebula glow is a relentless threat to these infant systems. It acts like a cosmic blowtorch, violently heating the outer layers of the gas and dust disks, driving material away in those long, streaming tails we observe. For a disk orbiting too close to the trapezium stars, this photoevaporation can strip away its mass at an alarming rate, potentially robbing it of the raw material needed to form gas giants like Jupiter or Saturn. Even if rocky, Earth-like planets manage to coalesce from the dust closer to the star, their young atmospheres would be bombarded by that same intense radiation, which could scour them away before they have a chance to stabilize. The challenge is immense, like trying to build a house of cards in a hurricane. Yet the universe is ingenious, and planetary formation may find a way in the quieter corners of these systems. While the outer regions of a disk are being eroded, the inner sanctum, within a few astronomical units of the central star, is shielded by the disk's own thickness and the star's gravity. Here, in a comma zone, dust grains can still collide and stick, building up planetesimals that could eventually become rocky worlds. Furthermore, many of these proplyds are located at varying distances from the nebula's core. Those on the outskirts, farther from the direct blast of the most massive stars, experience a much gentler environment. Their disks may survive long enough for the full planetary formation process to play out, from dust to pebbles to protoplanets. There is also the dimension of deep time to consider. The massive trapezium stars are brilliant but short-lived. Within a few million years, they will explode as supernova, their violent deaths clearing away much of the remaining gas and ending the era of intense ultraviolet bombardment. The lower mass, sun-like stars at the hearts of the proplyds, however, will live for billions of years. Their disks, having weathered the initial storm, could then enter a more peaceful era. Planet formation might continue or even accelerate in the aftermath, using the material that survived the early chaos. Imagine a scenario where the initial fury carves and limits the disk, but the quiet that follows allows for a second act of construction. We could be looking at solar systems where planets are predominantly rocky, their gas envelopes stripped away, or systems with giant planets that formed quickly and migrated inward before the disk evaporated. The Orion Nebula, therefore, presents not one future but a spectrum of possibilities. It is a grand experiment in extreme planet formation, showing us that the path to building worlds is not a single recipe, but a dynamic negotiation between the creative force of gravity and the destructive power of starlight. While the current nebula blazes with the light of newborn stars, its future is being written in pockets of profound cold and shadow. Scattered throughout the vaster Orion molecular cloud are dense, inky blotches known as infrared dark clouds. Seen from our perspective, they appear as stark silhouettes, black voids against the faint, warm glow of the Milky Way's background light. But this darkness is not an absence, it is a concentration, a cosmic womb so thick with gas and dust that not even infrared light can escape from within. These are the coldest places in the nebula complex, with temperatures plunging to just a few tens of degrees above absolute zero. Within these frigid, lightless clots, gravity works in silence. The extreme cold allows atoms and molecules to move slowly, reducing the internal pressure that would otherwise resist collapse. This means the gas can condense into incredibly dense knots, each one a potential stellar embryo weighing hundreds or even thousands of times the mass of our Sun. They are the mysterious precursors to the next great act. An infrared dark cloud is not yet a star-forming region in the classical sense. There are no brilliant jets or glowing cores. It is a pre-stellar core, a massive reservoir of raw material in the final stages of quiet accumulation, gathering itself for the inevitable, violent ignition to come. In a million years, the heart of one of these dark clouds will begin to heat under the strain of its own gravity. A massive protostar will flicker to life, buried so deep that its light will be trapped for eons, only escaping once its fierce radiation and winds finally blow apart its dusty cocoon. When that happens, a new blister of ionized gas will erupt onto the scene, a future Orion Nebula in the making. These dark silhouettes are therefore more than just shadows. They are the blueprints for tomorrow's cosmic fireworks, the hidden seeds from which the next generation of stellar giants and their luminous nurseries will grow. Deep within that seething X-ray glow from the young stars, a pattern may be hiding. A handful of studies have reported a strange signal, hints that groups of stars in the Orion Nebula cluster might be flaring in sync. Not just random outbursts, but coordinated bursts of high-energy activity, as if an invisible conductor cued a section of the orchestra to play a violent note in unison. The idea is tantalizing, suggesting a level of interconnectedness between stars that challenges our view of them as isolated islands in space. If true, what force could possibly orchestrate such a symphony of stellar tantrums? One compelling theory points to the nebula's vast magnetic scaffold. We know powerful magnetic fields thread through the entire region, connecting stars to the surrounding gas in a complex, invisible web. It is possible that a massive magnetic disturbance, perhaps a reconnection event within the nebula's turbulent plasma, could send a shockwave rippling along these field lines. That sudden change in the magnetic environment could simultaneously trigger instability in the coronae of multiple young stars, like plucking a single taut wire and making dozens of tuning forks hum in response. Another possibility involves a central triggering event. Imagine a powerful flare from one of the most massive stars in the trapezium, or a sudden influx of material from a disrupted protoplanetary disk falling onto a young star. The blast of radiation or a shockwave from such an event could sweep across the cluster, compressing the magnetospheres of other stars and inducing flares in a domino effect. Yet, the most cautious explanation is also the simplest: coincidence. With hundreds of magnetically hyperactive young stars crammed into the cluster, all flaring frequently and randomly, statistics alone suggest that sometimes several will erupt by pure chance in a narrow window of time. Our pattern-seeking brains might then stitch those random events into a meaningful sequence where none exists. This is precisely why the claim remains deeply controversial. To confirm synchronization, astronomers need to observe many repeated instances of the same groups of stars flaring together, ruling out random chance with extreme statistical certainty. So far, the evidence is sparse and not yet definitive. The search continues, a meticulous effort to distinguish a true cosmic chorus from the cacophony of a stellar nursery. If proven, synchronized flaring would reveal a universe where stars are not just neighbors, but participants in a shared, energetic dialogue, their furies linked by the invisible threads of magnetism that bind the nebula together. The synchronized flaring of stars would be a fleeting conversation within a dialogue spanning eons. To grasp the true scale of the Orion Nebula, we must step outside of human time and witness its story not as a single event, but as a perpetual, grand cycle of cosmic recycling. This is a timeline measured in hundreds of millions of years, a loop where death directly fuels new birth. It begins with an ending. Long before the trapezium stars flickered to life, other massive stars lived and died in this region of our galactic arm. Their lives were brief and brilliant, and their deaths were cataclysmic. In supernova explosions of unimaginable power, these ancient giants blasted their chemically enriched guts across light years. Heavy elements forged in their cores, carbon, oxygen, silicon, iron, were violently scattered into the void. This ejected material, mixed with primordial hydrogen and helium from the Big Bang, slowly cooled and gathered through gravity, coalescing into a vast, dark molecular cloud. That cloud is the true parent of everything we see. The Orion molecular cloud, with its dense filaments and cold cores, is not just a cloud, it is a graveyard and a treasury built from the ashes of its stellar ancestors. Within that dark treasury, gravity begins its slow work. Dense knots within the cloud collapse under their own weight, fragmenting into the seeds of new stars. This is the chapter we are witnessing now. The trapezium cluster ignites, its fierce ultraviolet radiation lighting up the surrounding gas like a match struck in a cavern. Protoplanetary disks swirl, cometary knots are shaped by the stellar wind, and the ingredients for new worlds are forged in the chaos. The nebula's glorious glow is the middle of the story, the brilliant and violent adolescence of this stellar family. But this phase is fleeting. The massive stars at the heart of this drama are living on borrowed time. In just a few million years, a cosmic blink, they will exhaust their nuclear fuel. Their cores will collapse, and they too will explode as supernova. Their deaths will be far more violent than their births. The shockwaves from these explosions will rip through the remaining molecular cloud, compressing some regions to trigger a new wave of star formation while violently dispersing others. This is where the loop closes. The material ejected from those future supernova, the newly forged heavy elements, the dust grains created in their cooling outflows, will be blasted back into the surrounding interstellar medium. It will mix with the debris from earlier generations and the gas that managed to survive the blast. Over millions of years, this enriched material will again cool, gather, and gravitationally collapse. New dark clouds will form, denser and more chemically complex than the last. Within them, new protostars will ignite, this time born from a cloud already seeded with the elements for rocky planets and potentially the chemistry for life. The iron in your blood, the calcium in your bones, the oxygen you breathe, atoms like these will be part of that future mix. The Orion Nebula we admire today is therefore not a permanent structure, but a single, luminous frame in a never-ending film. It is both a product of ancient stellar death and a nursery for stars whose own deaths will build the next cosmic generation. We are witnessing the universe's most profound economy, where nothing is wasted and every ending is written into the blueprint of a new beginning. That grand cycle of cosmic recycling is a story written in starlight, but it is also a story we have been telling ourselves for millennia. Long before telescopes revealed its swirling gas, the Orion Nebula was already a point of intrigue in the human sky. To the ancient cultures that traced the hunter's belt, that faint, fuzzy middle star in his sword was more than a smudge. It was a mystery waiting for a name. Some saw it as a celestial flame, others as the hunter's glowing weapon, an eternal symbol of power suspended in the heavens. This instinct to see meaning in its unresolved light is the nebula's first and most enduring cultural impact. It marked a boundary in the ancient mind between the fixed, orderly stars and something else, something nebulous and unresolved. That very quality made it a perfect canvas for myth, a place where human imagination could project stories of divine fire and cosmic battle onto the unknown. When the first crude telescopes turned toward it in the early 17th century, that mystery only deepened. What had been a point of light resolved into a cloud, a great nebula. To early observers like Christian Huygens, who produced the first known sketch of its inner structure, this was a profound revelation. The heavens were not just points of light on a crystal sphere, they contained texture, depth, and substance. The Orion Nebula became the prime example that the cosmos was filled with these milky, mysterious fluids, challenging the Aristotelian idea of a perfect and unchanging celestial realm. It became known simply as the Great Nebula, a title of respect that held its place for centuries as the most spectacular and scrutinized object of its kind. Every astronomer with a new, better telescope felt compelled to point it at Orion, each drawing adding more detail, more complexity, and more questions. Was it a swirling fluid condensing into a solar system, as Immanuel Kant and Pierre Laplace speculated? Or was it a distant island of stars too faint to resolve? This debate, centered so often on Orion, drove the science of astronomy forward. It made the nebula a living puzzle at the heart of the greatest question: what is the true scale and nature of our universe? The answer, when it came with photography and spectroscopy, was more wondrous than anyone had dreamed: a stellar nursery illuminated from within. Yet, even as science explained its physics, the nebula lost none of its power to inspire. It became a beacon for artistic imagination, its ethereal shapes and luminous colors translated into paintings, poetry, and music, representing both the sublime beauty and terrifying vastness of space. From myth to science to art, the Orion Nebula has served as a constant mirror. We look at its glow and see our own evolving understanding reflected back, a testament to our endless need to find meaning in the light and to let that mystery propel us closer to the stars. Those ancient stories of celestial fire find a modern echo in a signal we have only just learned to hear. From the depths of the Orion complex, radio telescopes have occasionally picked up something startling, not the steady whisper of ionized gas, but sharp, unexplained bursts of energy. These are not the famous fast radio bursts that arrive from distant galaxies, but they are their mysterious local cousins, fleeting radio flashes that last mere milliseconds and then vanish without a trace. Their origin is a complete puzzle, a transient event hidden within the nebula's constant radio hum. Why would such a dynamic, violent nursery produce these sudden, brilliant pops of radio light? The theories point to the most extreme physics imaginable happening in the shadows. One prime suspect is a young, hypermagnetic star known as a magnetar. Imagine a newborn stellar remnant, a neutron star with a magnetic field a quadrillion times stronger than Earth's, spinning rapidly within the dense cloud. Such a field, constantly stressed and tangled, could suddenly snap in a colossal flare, releasing a tsunami of energy that ripples through the surrounding plasma and blasts out as a coherent radio pulse. Another possibility lies in the very process of star birth itself. The final, violent collapse of a massive protostar's core, the moment it ignites fusion and becomes a true star, could release a gravitational shockwave so powerful it briefly energizes the surrounding magnetic field, creating a single, brilliant radio scream. Or perhaps the bursts come from chaotic interactions within the nebula's own turbulent plasma. When a supersonic jet from a young star plows into a dense knot of gas, or when two shock fronts from different stellar winds collide, the resulting turbulence could accelerate electrons to near light speed in an instant. These electrons, spiraling wildly in magnetic fields, might then emit a brief, focused burst of synchrotron radiation right in the radio band. What makes Orion the perfect hunting ground for such events is its sheer density of energetic processes. It is a cosmic pressure cooker where every ingredient for radio violence is present and constantly mixing: powerful magnetic fields, dense ionized gas, supersonic outflows, and a population of volatile young stellar objects capable of sudden, catastrophic releases of energy. For now, these radio bursts are rare and poorly understood ghosts in the data, but they represent a new frontier. Astronomers are now designing monitoring campaigns that will stare at Orion with radio eyes wide open, waiting to catch the next flash. Each unexplained burst is a potential key, a millisecond-long cipher that could unlock the physics of the nebula's most hidden and instantaneous acts of violence. Those fleeting radio bursts might be the explosive punctuation marks in a far more complex sentence written in magnetic force. The magnetic fields that thread the Orion Nebula, long mapped as simple, orderly lines, are now revealing a hidden layer of profound complexity. Advanced studies in magnetohydrodynamics, the science of how magnetic fields interact with hot, charged fluids like plasma, suggest these fields are not static rails. Instead, they are dynamic, living structures that can twist, tangle, and braid around each other like the strands of a colossal, invisible rope. This braiding is not a decorative feature, it is a fundamental engine. Imagine taking two separate strands of magnetic force, each a line of immense power, and winding them tightly together. As they twist, they store titanic amounts of energy, much like winding up a rubber band or coiling a spring. The tension builds silently within the nebula's plasma, a reservoir of pent-up power woven into the fabric of space itself. This stored energy cannot remain trapped forever. Eventually, the braided fields reach a breaking point. They can snap and reconnect in a violent process known as magnetic reconnection. In an instant, all that stored magnetic energy is converted into other forms, a furious release that can manifest as intense heat, powerful particle acceleration, and explosive flares. This single mechanism offers a beautifully unified explanation for many of the nebula's most violent phenomena, those sudden, brilliant X-ray flares from young stars. They could be the result of braided magnetic fields in the star's own coronae suddenly reconnecting. the focused supersonic jets screaming from protostars. Their incredible collimation, the way they stay narrow over vast distances, could be directly due to the guiding and pinching force of braided magnetic field lines anchored in the star's rotating disk. Even the diffuse, million-degree X-ray glow that permeates the nebula's cavities might be partly heated by countless tiny reconnection events happening continuously in the braided fields stirred up by colliding stellar winds. This transforms our view of the nebula from a place where separate events happen to a single, interconnected system where magnetism is the active conductor. The braiding provides a hidden wiring diagram, a way for energy to be transported, stored, and then violently released across different scales, from the surface of a single star to the vast cavities between them. It suggests the nebula's beauty is not just illuminated by starlight, but animated by the silent, coiling, and occasionally snapping tension of magnetic ropes we are only beginning to perceive. The magnetic braiding that powers the nebula's violence is not an isolated event, but part of a galaxy-wide metabolic system. To truly appreciate the Orion Nebula, we must see it not as a solitary wonder, but as a vital organ in the living body of the Milky Way. It is a galactic engine, one of countless similar forges, responsible for the most fundamental cycle of cosmic renewal. This engine runs on a simple, three-part process, and Orion is a perfect, active example of each stage. First, it converts the galaxy's raw fuel. The nebula draws in vast reservoirs of cold, primordial hydrogen and helium, the leftover gas from the Big Bang that still drifts between the stars. Through gravity and turbulence, it compresses this simple gas into the dense cores where nuclear fusion ignites, literally transforming ancient, inert material into brilliant new suns. This is the galaxy's way of turning its basic hydrogen fuel into structured, luminous energy. Second, it enriches the galactic ecosystem. The stars Orion creates do not just shine, they cook. In their cores, nuclear fusion forges heavier elements, from the carbon in our cells to the iron in our blood. During their lives, massive stars blow fierce winds, seeding their surroundings with these new elements. And when they die in supernova, they detonate, scattering their chemically enriched guts across light years. The nebula itself becomes a mixing bowl, churning these newly forged metals back into the surrounding gas. This means the next generation of stars and the planets that form around them will be born from material that is no longer pristine, but enriched with the building blocks for rocky worlds and potentially life itself. Finally, Orion's engine provides critical feedback. The intense radiation and powerful winds from its young stars do more than just create beautiful shapes, they regulate the very process that birthed them. These forces blow gigantic bubbles, carve cavities, and create shockwaves that compress nearby clouds to trigger new star formation, while simultaneously dispersing and eroding other clouds, shutting down star birth elsewhere. This feedback loop acts as a galactic thermostat, preventing all the gas from collapsing into stars at once in a single, brief burst. It ensures star formation is a slow, sustained process, spread out over billions of years, allowing for the long, stable lives of solar systems like our own. So when you look at Orion, you are seeing more than a nursery, you are witnessing a cornerstone of galactic ecology. It is a factory that builds stars, a refinery that creates complex elements, and a regulator that controls the pace of cosmic evolution. The beauty of its glow is a side effect of its essential work, the visible signature of our galaxy breathing, growing, and recycling itself on a scale almost beyond comprehension. This brilliant galactic engine, however, has a built-in expiration date. The Orion Nebula's future is written in the very stars that give it life, a fate that is both spectacular and final. Within a cosmic blink, perhaps only 2 or 3 million years from now, the massive trapezium stars will reach the end of their short, furious lives. Having burned through their nuclear fuel at a prodigious rate, their cores will collapse, triggering some of the most violent explosions the local galaxy will ever witness. One by one, these stellar titans will die as supernova. Each detonation will unleash more energy in a few weeks than our Sun will produce in its entire 10 billion-year lifetime. The shockwaves from these blasts will be the nebula's own undoing. They will rip through the remaining veils of glowing gas and the dark molecular cloud behind it with unimaginable force. The delicate structures we marvel at today, the sculpted pillars, the evaporating propellids, the luminous bar will be shredded and swept away. The beautiful, intricate cloud of gas and dust will be violently dispersed, its material blasted back into the interstellar medium from whence it came. What will be left is not a nebula but a glittering skeleton. The supernova will leave behind their dense, collapsed remnants, neutron stars, or perhaps even black holes hidden among the surviving stars. The lower mass, Sun-like stars, the propelled central stars that endured, will remain. They will no longer be shrouded in glowing mist, but will shine as a brilliant, loose open cluster against the black velvet of space, a cluster initially still bearing the name of the Orion Nebula. But even this cluster is not permanent. Without the gravitational glue of the massive gas cloud that once bound them together, the stars will slowly, over hundreds of millions of years, drift apart on their own galactic orbits. Their family ties severed by physics, they will go their separate ways, becoming solitary wanderers in the Orion Arm, their shared birthplace forgotten. The glorious visible phase, the era of the great glowing cloud, will be over. The nursery will have closed, its children grown and scattered. Yet this end is not an absolute conclusion, but a transformation. The material blown away by those final supernova will not vanish. It will travel outward, carrying with it a rich harvest of heavy elements forged in the stellar furnaces and explosions. This enriched debris will eventually mix with other galactic clouds, becoming part of the raw material for a future generation of stars, planets, and perhaps even life. The Orion Nebula, in its death, will sow the seeds for nebulae yet unborn. The nebula's ultimate fate is not an end, but a transformation into a different kind of record. This brilliant cloud, for all its violence and change, serves as a profound and unique snapshot in time, because it sits in our own galactic backyard, a mere 1,300 light-years away. We are granted a front-row seat with a clarity impossible for more distant stellar nurseries. We are not seeing a blurry, generalized concept of star birth. We are witnessing the specific, intricate details of the process as it unfolds right now, with a resolution that lets us pick out individual evaporating disks, trace the paths of supersonic bullets, and map the chemical makeup of its warm gas. This incredible detail freezes a moment. The entire luminous structure we call the Orion Nebula is a transient bubble, a blister on the face of the dark molecular cloud. The intense ultraviolet light that makes it glow has only been streaming out from the trapezium stars for a brief window, perhaps just 20 or 30,000 years. In cosmic terms, that is less than a single heartbeat. We are catching this expansive nursery in a specific, fleeting phase, after the first massive stars have ignited, but before their explosive deaths have reshaped the landscape entirely. It is a snapshot of stellar adolescence, a chaotic and brilliant growth spurt captured in mid-stride. This makes it an irreplaceable time capsule. Within its glowing folds, we see all the stages of the story simultaneously, from the cold, dark clouds that are the future, to the violent birthing jets of the present, to the massive, shining stars that are the recent past. We can study the conditions that were present when our own sun and solar system formed over 4.5 billion years ago, because the physics is the same. Every propelid is a potential blueprint for our own origins. Every molecule detected in the hot core is a clue to how the ingredients for life are scattered into young planetary systems. The nebula is not a static museum piece, but a single, brilliantly illuminated page torn from the continuous, eons-long story of our galaxy's evolution. It is our clearest window into the universal forces of creation and destruction, a time capsule sent to us not from the distant past, but from the ongoing, magnificent present of the cosmos. That single, brilliant page in the cosmos holds a profound lesson about our place in the universe. We have journeyed through 50 of its strangest secrets, from geometric ghosts and chemical cauldrons to supersonic bullets and spinning diamonds. Each one peels back a layer of the familiar, revealing that the Orion Nebula is not a serene painting, but a dynamic, violent, and chemical-rich cosmic laboratory. It is a battlefield where light sculpts gas, a factory forging the elements for life, and a graveyard for ancient stars, all operating within a hidden scaffold of magnetic force. This is the reality behind the beautiful glow. Every mystery we solve here, from the lithium problem in infant suns to the source of the anomalous microwave whisper, does not bring finality. Instead, it reveals 10 new questions, pulling us deeper into the fundamental physics of creation. This relentless curiosity is what drives astronomy forward, turning a patch of light in a hunter's sword into a gateway for understanding the birth of stars, planets, and perhaps life itself across the galaxy. So the next time you find yourself under a clear winter sky, look up, find the 3 stars of Orion's sword, and let your gaze settle on that faint, fuzzy middle one. Remember that within that soft glow rages a storm of unimaginable scale, where wonders beyond counting are unfolding in the dark. Which of its 50 strange phenomena captured your imagination the most? Was it the evaporating solar systems, the natural lasers, or the hidden supernova shrapnel in our own planet's crust? Share your thoughts below, and if you want to continue exploring the deepest mysteries of the cosmos, subscribe for more journeys to the edges of our